this thing on? Yeah, do you hear me? Okay. Do I want to continue?
It's recognizing your.
Yeah.
That's what. Try it.
Okay. There we go.
Now we have Kisun with symmetric tropic ring 2 matrices.
Yeah, thanks. Thanks for having me. I'm actually consider myself as a computational algebraic geometer, so I'm just happy that I can give my recent result about the combinatorics. So I'm just happy that I can talk about my combinatorial side of my research. So this is based on the joint work with May Kai and Josephine Yu. They are both at Georgia Tech, and this title is actually the paper on which is already on arXiv, which is under revision. I think that the title will be changed, but you can still find that arXiv versions using this title. So let me just begin. I know that talks already given in the morning is very tropical, just like the weather in Daejeon this week. But I just want to add one more piece of the tropical geometry again. So let me just give you a brief overview of the tropical algebra again. So I want to talk about tropical semi-ring. We work on the real number field, and then we define tropical summation and tropical multiplication. And tropical summation of these two numbers, x and y, is just taking the minimum. Of course, Felipe's talk, he used the maximum, but it depends on your preference. I use minimum. And the tropical multiplication is just defined by the just regular addition. So tropical sum is taking the minimum, tropical multiplication is taking the regular summation. And from this one, I'm interested in tropical matrix. I want to think about the concept of the rank, what's happening in this tropical setting. But let me just go back to the linear algebra. I want to talk about the concept of the rank. And here's the definition that I want to stick to. We say that matrix has rank at most R when R plus 1 minus or vanish. So this is of course, there are many different ways to define the rank, but I want to stick to this definition because it fits into our concept. But main goal for today is I want to understand the tropical counterpart of the rank, especially which is called tropical rank. So I will talk about this rank for the tropical setting in a slightly later. But I want to talk about the tropicalization. So what I want to do is, if you have some nice objects or concept in the algebraic geometry or linear algebra, I want to tropicalize them and I want to understand a little bit more combinatorially. So let me just talk about the tropicalization. Let's say that we have a field which is given by K and with a valuation. For example, you can just work with the complex number field with the trivial valuation, or sometimes you can work with the Piezo series field. Piezo series field means that you have a series expansion whose exponent can be a rational number. In this case, valuation will be just the degree of the minimum degree term in that way. So from this field, you can define a polynomial, of course, in this form. You can define a polynomial in this way. Of course, you can, more generally, you can also consider Laurent polynomial if you're allowed to have an integer exponent. But what I want to do is I want to define the tropicalization of the polynomial. What I did was I just replaced everything by tropical summation and tropical multiplication. So if you see this monomial, this goes to the summation here because we just replace everything by the tropical summation, a tropical multiplication. And this C alpha coefficient goes to the valuation. And then we are taking summation, so the tropicalization goes to the minimum. So this is just really the replacing everything by tropical sum and tropical multiplication. We will record this as tropicalization of the polynomial. I wish this makes sense. But I want to talk about the tropical variety. But let me just go back to the simplest variety that we can think about, which is the tropical hypersurface, because it will be defined by only one polynomial. Let me define tropical hypersurface in this way. What I want to do is, we have a tropicalization of the polynomial. I want to collect all the points in R to the n such that minimum of this tropicalization attained at least twice. This is how we define the tropical hypersurface. So let me just give you an example. We have f equals to x plus y plus 1, and then let me just try to draw the tropicalization of this. What is the tropicalization of this guy? It is, I'm just taking the tropical summation and multiplication, then you have this minimum of these three. X, y, valuation of 1 goes to 0, so we have a minimum of these three things. Now we want to take the minimum at least twice. If you attain the minimum and y and 0, then you have this half horizontal lines. If you attain the minimum and x and 0, then you have a vertical half line. And if you have x, y minimum, then it must be less than 0, so it goes to the negative direction of the diagonal. So we have this tropical hypersurface drawn in from this example here. So from this tropical hypersurface, we can also define tropical variety. Suppose that you have an ideal, which is defined over the polynomial ring. Then you have a variety from this, and then we can define the tropical variety in this way. Just taking the intersection of the tropical hypersurface from the OR polynomial inside the ideal. This is how we define the tropical variety. Maybe I can say why I want to care about the tropical geometry. So what I want to do is, by taking the tropicalization, I want to study compute the combinatorial invariance of some variety that you are interested in. Suppose that you have some algebraic variety, which is quite hard to compute, then you can tropicalize that, then you can understand the combinatorial and polyhedral property of that. So I just want to do some combinatorial understanding of the algebraic geometry, and this is probably quite nice motivation for the tropical geometry. So in order to talk about this more, I want to mention structure theorem again. So tropical variety, you don't really need to read this statement here, but what I want to say is, if you have a irreducible variety, and its tropical variety has a nice polyhedral structure. So when you have a variety, by taking the tropicalization, then you can understand that variety in terms of the polyhedral geometry and combinatorics. So this is why I was really excited to study the tropical geometry. Now I want to talk about rank in the tropical setting. I want to talk about the tropical rank. I wish you remember the definition of the rank that I mentioned before, but I want to talk about tropical rank. Matrix has tropical rank at most R when the R plus 1 tropical minors vanish. So this is the definition that I want to use. Of course, there are many different concepts of rank in the tropical setting, but I want to use this definition. I just want to stick with the tropical rank today. For example, let's say that you have a 3 by 3 matrix whose entries are given by x11 up to x33. Then let's think about 3 by 3 minor, for example. I guess this font is not designed to be read, but this is your 3 by 3 minor. But I want to tropicalize this by replace everything by tropical summation and multiplication. And I want to attain the minimum at least twice. Therefore, this is nothing but just minimum of these 6 terms. 3 by 3 minors have 6 terms, and I want to find out the minimum of these 6 expressions at least twice. So, okay. Let me give you an example. We have this identity matrix, and I want to determine the tropical rank of this matrix. So what is the term of the tropical minors? Let's consider these terms of the matrix. This expression is one of the terms in the tropical minor. Obviously, matrix has non-negative entries, so therefore it must be 0, and this is the minimum. Likewise, if you consider these terms of the tropical minor, they also attain its minimum, which is a 0. Because minimum is attained twice, therefore we say that 3 by 3 minor vanish, so the tropical rank is 2. This is how we consider the tropical rank of the matrix. However, I want to talk about symmetric tropical rank. I want to think about symmetric matrix now. I want to assume symmetry. We say that symmetric tropical rank is at most R when R plus 1 tropical minors vanish, including symmetric minors. Let me explain with an example. Suppose that you have a same matrix. Suppose that you have a same identity matrix. However, if you look at this one, if you assume symmetry, you know that x12 must be x21 if you assume symmetry. x23 must be equal to x32. x31 must be equal to x13. So even though this matrix it seems like we have a minimum at least twice. However, minimum is just obtained only once. Therefore, symmetric tropical rank is not 2, but it is 3. Even though tropical rank is 2, its symmetric tropical rank is 3 because minimum is not obtained twice. So this is the meaning of we assuming symmetry. So let me just give you this example. This might be another example. And then if you think about this term, it goes to 0, which is the minimum. If you think about this term, which goes to 0, and even though you assume symmetry, we obtain the minimum twice. Therefore, symmetric tropical rank is 2. I wish this makes sense. And then what I want to do is I want to describe this type of rank 2 matrices combinatorially. And in order to do this, we will think about tropical convexity. So let's say that we have some set, capital S, which is contained in R to the n. And we will say that this set is tropically convex. If you take any xy from this S and AB should be any real number, if you consider tropical convexity expression ax plus by, if it is contained again inside capital S, then we will say that this set is tropically convex. So you can see that this ax plus by, this is a regular expression for the convexity. Of course, we can suppose that you have some set inside R to the n, then we can also consider tropical convex hull, which is the smallest tropical convex set containing this V, because I want to consider tropical convex hull of the columns of the matrix later. I want to add one more remark. If you consider tropically convex set and any vector inside capital S, it is allowed to add 1, 1, 1, 1, 1 vector. If you add 1, 1, 1, 1, 1 vector, then this vector or point must be also contained as S again. So because of this one, when you consider tropical convexity, it is quite natural to quotient out by 1, 1, 1, 1, 1 vector. Sometimes we call this as a tropical projective space. So from this tropical convex setting, now I want to describe how we can describe this matrix in terms of the combinatorially. Suppose that we have this matrix. Then we can think about this matrix. We can say that this matrix is equivalent. Because if you have 1, 0, 0, you can subtract 1, 1, 1 vector, then you got 0, negative 1, negative 1. If you consider the tropical convex hull of the columns of this matrix, then you got this union of the 3 thick line segments here. Union of these 3 thick line segments here. This is the tropical convex hull of the columns. So I want to point out that we have 3 different directions, x1, x2, and then let me just denote this direction by x0. Okay. So I want to introduce the result of Hannah Markowitz and Josephine Yu in 2009. They proved that the space of the tropical rank 2 matrices form a simplicial structure of the bicolor tree. Let me talk about how we construct this one. Suppose that we have this matrix. Then we have a tropical convex hull out of these columns. Then we will attach colored label on this tropical convex hull. What I want to do is, if you look at the first column, then we put the red one on this horizontal edge here. Likewise, but we want to also satisfy the balancing condition. In order to make this tree to be balanced, we put blue edges on here labeled by 1. And we do the same thing for the second column. And we do the same thing for the 0th column. You have a tree which is with the colored leaves with the labeled by numbers. So we call this as a bicolor tree. Okay? So the tropical rank 2 matrices can be described by this bicolor tree. This is the result in 2009. And here's our result. So space of the symmetric tropical rank 2 can be understood as the simplicial fan structure of the symmetric bicolor trees or symbic tree in short. So what I want to say is, suppose that we have this matrix. We already know that this matrix has a symmetric tropical rank 2. Then how can I draw this? This is a tropical convex hull. Let me just label them by blue by using from the balancing condition. From the first column, we put label 1 on the vertical line segment here. And for the second column, we put 2 here. And then we put 0 here. So this is the symmetric bicolor tree. Let me talk about what is the meaning of symmetry. What I want to do is I want to take the symmetry about this line here. Can you see this dotted line? If you take this line, and if you take the symmetry about this line, this red one goes to blue one, blue 2 goes to red 2, etc. So even though you symmetry, if you rotate about this line here, you still keep the symmetry. That's why we call this a symmetric bicolor trees, because these will not be happen from this one. If you look at this matrix, this is the symmetric tropical rank 3. If you look at this one, if you rotate by this line, red 2 does not go to blue 2 because they are on the same side. So it is not symmetric. So whenever you have a symmetric tropical rank 2 matrix, you can find out the corresponding symmetric bicolor tree. So this is our theorem. One more small technical remark is, of course, this matrix will be obtained by from this tree when you assume that this point O is located at the origin. But of course, you can more generalize this. If you want to translate this point wherever you want, then it is just the same as adding this matrix for some proper number D, E, and F. So you can also generalize this type of statement here. So here's the figure for the 3x3 symmetric tropical rank 2 matrices. This is the description of that. Of course, depending on the size, you have a different diagram. Maybe this is the easiest possible case that we can draw. Let me talk about the results out of it. So first of all, I want to talk about shellability. In their result, Hana, Marco, and Josmin, you proved that this space of rank 2, tropical rank 2 matrices is shellable. And we also proved the same thing. The space of the symmetric tropical rank 2 matrices is shellable as well. So it means that it has a homotopy type of the wedge of the spheres. So from the combinatorial, from the polyhedral structure that we get, we consider this a tropical, topological property. This is the first result of the shellability. And I know that my talk was somehow deceptive because I never talked about matroid. So now it's time to talk about the matroid. I want to define the matroid from these Symbic trees. But before I talk about the matroid, before I really define this, I want to talk about the motivation. This problem is motivated by the matrix completion problem. Let me talk about the example. We have a matrix here. But this is a partial matrix, which means that some entries are unknown. X, Y, Z are unknown entries. What I want to do is, can you complete this matrix to have a rank 2? Can you do this? Can you find that the proper number X, Y, Z such that this matrix has a rank 2? This is the matrix completion problem. You want to complete the partial matrix in order to satisfy some desired property. Why we are care at this one? Because Daniel Irving Bernstein in 2017, he used the tropical geometry in order to describe the basis of the algebraic matroid of the rank 2 matrices. From the 3x3 determinant, you have determined the ideal, and then we can consider algebraic matroid. And he described the basis of this algebraic matroid using the tropical geometry. Yes? So the question is it must be symmetric, skew-symmetric, and just the non-symmetric matrices? Okay, so yeah, that's why we want to stick to the symmetric matrix for this for our result. Okay, so this is I actually didn't write down the full sentence here, but he proved for regular non-symmetric matrix and the skew-symmetric matrix. So it means that what he did was he characterized the partial matrices that can be completed to be rank 2 matrix. Okay, so the hidden technical part that I want to say is. This was possible because we could use the tropical geometry because algebraic matroid is preserved under the tropicalization. That's why we can use the tropical geometry to understand this type of problem. So this is one technical remark that I want to give. Now, we are define the matroid for the Symbic trees. Suppose that we have Symbic tree with the 4 leaves here, and then we have corresponding symmetric tropical rank 2 matrix. This is the corresponding symmetric matrix. We have 7 parameters, A, B, C. They are parameterizing this edge length. D, E, F, and G. They parameterizing the location of this dot point here. So we have a symmetric tropical rank 2 matrix. From this one, we can make the really large matrix, which is obtained from this parameterization. Rows are labeled by these parameters, and then columns are labeled by entries. Then we have this large matrix. We call this as a distance parameter matrix. We consider linear matroid from this one, then this is the matrix for the symmetry. And then if you understand this one, then you can also understand the algebraic matrix for the symmetric rank 2, rank 2 symmetry matrices. Yeah. So, so basis of the Matroid symmetry is characterized as basis for the rank 2 symmetry matrices. This is what I want to say. And as I mentioned, Bernstein did for the rank 2 non-symmetry matrix as Q-symmetry matrix. So here's our result. The collection of the basis for the algebraic matrix of the regular rank 2 symmetry matrices, suppose that you have this type of algebraic matrix, its basis can be, collection of the basis can be understood as a union of the basis of some special tree, which is called trees with the caterpillar branches. So in order to characterize the basis for the algebraic matrix from the symmetric rank 2 matrices, you don't need to study all symmetries, but only specific type of symmetries, which is the trees with the caterpillar branches. So here's the caterpillar, and here's the caterpillar symmetry. What is the trees with the caterpillar branches? This is the tree in this type of form. So you have a tree with all the branches must be caterpillar. So if you understand all the basis of this type of tree, then that's the whole collection of the basis for the rank 2 symmetry matrices. Yeah, thank you. I'll stop here.
Any questions?
We need.
Oh, can you do this?
Okay. So my question is there? Is this? One-to-one correspondence between the symmetry and the symmetric matrix is just one-to-one, or do we need any equivalence relation?
So if you have a symmetric tropical rank 2, you can find out the symmetry, and then from the symmetry, if you consider the coordinates of it, then you can also find the corresponding symmetric tropical rank 2 matrix. Yeah. So it is somehow one-to-one correspondence.
Any other questions? What's scary about rank 3?
What's scary about rank 3? So one thing, yeah, that's a nice question. So why we could do this type of combinatorial description of it? Because if you have a symmetric tropical rank 2, if tropical convex hull forms something like a tree, because it's dimension one thing. But if you have a rank 3 or something like that, then there's no nice description of it. Or also, in order to think about rank 3, you should consider 4x4 tropical minor, and we actually don't know many things about the 4x4 tropical minors of it. So does that form a tropical basis or something like that? Yeah. Or in the rank 2, yeah, one more technical thing is, when the for 3x3 minors, you can say that symmetric coupler open rank is equal to symmetric tropical rank, so that you can also use this type of construction, but rank 3 we cannot. So even for rank 3, it is very, very chaotic.
Okay, thank you, Kisun. We are going to take a